Yesterday, October 16th, 2025, a newly released image of 3I-ATLAS sent scientists scrambling and deepened an already baffling mystery. In the image, 3I-ATLAS exhales a 6,000-kilometre plume pointed straight into the sun rather than away from it. This feat is so bizarre and unnatural it only points in one direction. Something built, not born. What is this object? Is it really a comet? Tonight, we untangle all the evidence step by step, and by the end what we discover not only rewrites comet physics, but offers a revelation nobody's ready for. If these mysteries pull at you the way they pull at me, don't just watch, be part of it. Tap like and subscribe so you're here for every twist as this story unfolds live before us. In the comments, tell me where you're watching from, what time it is there, and whether you think we're getting the whole truth, or just the version they want us to see. And if you want to push this conversation wider, share this video on X, Facebook, Reddit, or even just in your private chats. This channel exists because of you, and your support is what lets us keep chasing down the mysteries no one else will touch. Part 1, The Image That Shouldn't Exist. On October 16th, 2025, the astronomical world was shaken by something that should not be possible. An image appeared in the Astronomer's Telegram, processed from data collected on August 2nd and 3rd by the Tidy 2-meter twin telescope in the Canary Islands. What it showed was so fundamentally wrong, so physically backwards, that astronomers around the globe stopped what they were doing and stared. Picture this image in your mind. At the centre sits a black circular mask, blocking out the overwhelming glare of the object itself. Around that mask spreads a bright halo, the expected dusty coma that surrounds any respectable comet. But then, extending from this cloud of gas and dust, there's something else. A narrow jet, faint but unmistakable, stretching roughly 6,000 kilometres in projection. And here's where physics takes a holiday. This jet points directly toward the sun. You might be thinking, so what? Comets have jets all the time. They're spectacular, dramatic features that spray material into space as frozen volatiles sublimate under solar heating. But here's the thing that every undergraduate astronomy student learns in their first planetary science class. Comet jets always, and I mean always, point away from the sun. That's not a preference. That's not a tendency. That's a fundamental consequence of how radiation pressure and the solar wind work. The sun pushes. Material flows outward. The physics is as straightforward as water running downhill. Except here, the water appears to be running uphill. The jet from 3I-ATLAS, this interstellar visitor that's been captivating observers for months, defies that basic rule. Imagine watching a fountain where the water arcs backward into the nozzle, or seeing smoke from a fire drift down into the flames. That's the level of wrongness we're confronting. The anti-solar direction, the zone where jets and tails are supposed to flourish, sits empty or dim. Meanwhile, this sunward plume extends like an accusing finger toward our star. Scientists deal in models. We build frameworks that explain what we see, predict what we haven't yet observed, and occasionally crumble when nature reveals something we didn't account for. This image doesn't just challenge the comet model, it breaks it. If this feature is real, if it's not some elaborate trick of image processing or observational artifact, then we need to rewrite what we think we know about how these ancient travellers behave. The implications ripple outward like cracks in ice. Are we looking at a completely new class of object? Is there some exotic physical process occurring that we've never encountered in our own solar system's comets? Could this be evidence of something even stranger, something that makes the term comet inadequate for what we're witnessing? These questions don't have comfortable answers yet, and that's exactly what makes this moment so extraordinary. Before we dive deeper into what this means, we need to acknowledge the elephant in the telescope dome. Astronomical images, especially those teased out of faint signals using sophisticated processing techniques, can lie. They can show us ghosts, artifacts, patterns that exist only in the math rather than in physical reality. Laplace filtering, the technique used to enhance faint structures in this image, is powerful but not infallible. It can amplify noise. It can create false features from the way background stars trail across long exposures. Every astronomer worth their salt knows this, and the first response to any shocking image is healthy skepticism. So we won't just accept this blindly. We'll demand confirmation, multiple independent observations, different instruments and techniques all pointing to the same conclusion. But I'm telling you right now that confirmation exists. It's been building for weeks. Earlier observations hinted at plumes extending at odd angles, at position angles around 280 degrees that didn't match expectations. The Hubble Space Telescope caught glimpses of asymmetric features. Ground-based telescopes in multiple countries saw hints of the same orientation. This isn't one telescope having a bad day. This is multiple eyes on the sky, using different technologies, all seeing something similar. The community hasn't fully converged on absolute certainty. Science rarely offers that luxury, but the consensus is shifting from probably an artifact to likely genuine to we need to explain this thing. When astronomers start publishing papers that discuss the sunward jet as a real feature requiring real explanations, you know we've crossed a threshold. We've moved from skepticism to acceptance, from dismissal to fascination. What comes next will determine whether this object rewrites our understanding of small bodies in space, or whether it opens doors we didn't even know existed. The clock is ticking. Within days, 2 spacecraft will sweep through nearby space, their instruments potentially capturing data that could confirm or demolish our interpretations. But before we get to that moment, we need to understand just how deep this rabbit hole goes. Because the sunward jet, that's just the beginning. The chemistry pouring out of this thing tells a story that makes the jet look almost mundane by comparison. Part 2. Confirming the sunward plume. Before we let ourselves believe in the impossible, we have to eliminate every possible mundane explanation. That's the scientific method's greatest gift and most frustrating requirement. When you see something extraordinary, your first job isn't to celebrate, it's to doubt. So let's doubt intelligently. Image processing in astronomy is part art, part science, and part forensic investigation. You're taking photons that travelled across interstellar space, struck a detector, got converted to electronic signals, and now you're mathematically manipulating those signals to reveal structures too faint for the eye to see directly. Every step introduces opportunities for error. Background noise can masquerade as real features. Cosmic rays hitting your detector leave bright streaks that look like jets. Stars trailing across long exposures create lines that might align by pure chance with interesting directions. Deconvolution algorithms, which try to sharpen blurred images, can ring and artifact in ways that generate false structures. The teams analysing 3I-ATLAS know all this. They've been doing this work for decades. They didn't just run the image through a filter and call it a day. They checked for background star contamination. They examined multiple epochs of observation to see if the feature persisted or changed, in ways consistent with a real physical plume versus a processing ghost. They compared results from different telescopes with different optical systems, different detectors, different atmospheric conditions. They looked at the raw data before any processing, searching for the faint signal that would confirm something real existed before the enhancement algorithms touched it. What emerged from this gauntlet of skepticism was increasingly hard to dismiss. Earlier observations in late July and early August had already hinted at peculiar plumes extending at position angles that shouldn't make sense for normal cometary activity. Position angle, for those unfamiliar, is how we measure direction on the sky, with 0 degrees pointing north, 90 degrees pointing east, and so on. The antisolar direction, where comet tails traditionally point, sits at a predictable position angle based on the geometry of the comet's orbit and the Sun's location. For 3I-ATLAS, during those observations, that antisolar direction should have been nowhere near where this jet appeared. Multiple research groups began cross-checking their data. The Hubble Space Telescope, with its exquisite resolution above Earth's turbulent atmosphere, had captured images showing asymmetric coma structure. Ground-based observatories in Spain, Chile, and Hawaii independently noted unusual features. None of this happened in a vacuum. Astronomers talked to each other, share data, compare notes. When multiple independent teams start seeing similar oddities, the artifact explanation becomes increasingly strained. Think of it like witnesses to an unusual event. If one person tells you they saw something strange, you're rightly skeptical. If 10 people scattered across a city all describe seeing the same strange thing from different vantage points, using different cameras, at slightly different times but with consistent details, now you're obligated to take it seriously. That's where we are with the sunward jet. Too many eyes, too many instruments, too much consistency. The technical details matter here because they're what separate wild speculation from grounded observation. When scientists use Laplace filtering, They're essentially looking for edges and discontinuities in brightness. It's like turning up the contrast on an image to make faint details visible. But that technique is well understood. We know what artifacts it produces. We know how to distinguish between real features and filter-induced ghosts. The sunward jet shows characteristics consistent with a real, three-dimensional structure extending from the nucleus, not a flat processing artifact. Some researchers went further, analysing the spectral signature of the material in different parts of the coma. If the jet is real, its spectrum should show the same molecular emissions as the rest of the coma, just perhaps in different ratios depending on what's being preferentially ejected. And sure enough, spectroscopic data supported the presence of material in that sunward direction, not just empty sky with noise. You can't fake molecular emission lines easily. Either the molecules are there, fluorescing in sunlight, or they're not. So where does this leave us? The scientific community has moved from initial disbelief to cautious acceptance. Papers are being written that assume the sunward jet is real and focus on explaining it rather than explaining it away. That's a significant shift. It means we've crossed the threshold from "is it real?" to "okay, it's probably real, so what does it mean?" And that second question is far more interesting and far more unsettling. Because if the jet is real, if material truly is streaming toward the sun, in defiance of everything we thought we understood about cometary physics, then we need to ask what's coming out of it. We need to look at the chemistry, the composition, the fingerprints of whatever substance is creating this backwards fountain. And when we do, when we turn our spectrometers toward 3I-ATLAS and analyse the light it emits, we find something almost as strange as the jet itself. We find nickel where there should be iron, carbon dioxide where there should be water, and ratios that make no sense for a normal comet. The jet might be the most visually striking anomaly, but the chemistry, that's where things get truly weird. Part 3. Nickel without iron. If the jet is real, and we're increasingly confident it is, then the next obvious question becomes unavoidable. What exactly is streaming out of this thing? When we look at comets, we're essentially doing forensic chemistry at a distance. Light from the sun hits molecules in the coma, exciting them to higher energy states, and when they relax back down, they emit photons at very specific wavelengths. Each molecule has its own unique fingerprint, a spectrum as distinctive as a barcode. By spreading that light into its component colours and measuring the intensity at different wavelengths, we can identify what chemicals are present and in what relative amounts. Astronomers pointed some of humanity's most powerful spectrographs at 3I-ATLAS. The very large telescope in Chile, equipped with a UV spectrograph, captured high-resolution spectra across multiple epochs as the comet approached the Sun. What those spectra revealed was, to put it mildly, unexpected. Strong emission from neutral nickel atoms dominated certain parts of the spectrum. This wasn't a subtle hint or a marginal detection. This was a clear, unambiguous signal shouting, "Nickel is here." Now, finding metals in comets isn't inherently shocking. Comets contain dust grains, and those grains include refractory elements, things like iron, magnesium, sodium, nickel, and calcium. When dust sublimates, or when solar radiation is intense enough, these metals can appear in the gas phase and emit their characteristic spectral lines. What's shocking about 3I-ATLAS is the ratio. Specifically, the nickel to iron ratio makes no sense. In normal solar system comets, when you detect nickel, you also detect iron, and you detect it in ratios that roughly reflect cosmic abundances. Iron is more common than nickel in the universe. It's more common in meteorites. It's more common in practically every astronomical context we've ever studied. You expect to see more iron than nickel, not the other way around. But in 3I-ATLAS, observers found epochs where nickel emission was strong and iron emission was nearly absent. Not just a little weaker. Absent. Gone. Missing in action. The technical term scientists use is extreme abundance ratio. That's academic speak for, this is really, really weird. Some observations showed nickel to iron ratios orders of magnitude higher than anything seen in other comets. It's as if someone took a normal comet, carefully filtered out most of the iron, and left the nickel behind. Nature doesn't usually operate with that kind of selectivity. But wait, the chemistry gets stranger. The James Webb Space Telescope, that marvel of infrared astronomy now revolutionizing our view of the universe, turned its instruments toward 3I-ATLAS. JWST specializes in infrared wavelengths, perfect for detecting molecules like water, carbon monoxide, and carbon dioxide. What it found was a coma dominated not by water, as you'd expect from a typical comet, but by carbon dioxide. The carbon dioxide to water mixing ratio came in at roughly 8:1. Let me say that again, 8 times more carbon dioxide than water. For context, most solar system comets are essentially dirty snowballs, with water ice being the dominant volatile. Sure, they contain carbon monoxide, carbon dioxide, methane, ammonia, and other frozen gases, but water usually wins by a comfortable margin. It's the substance that sublimates most readily at the distances where comets typically become active. Comets with high carbon dioxide ratios exist, but they're rare, and even among those unusual cases, 8:1 stands out as extreme. What could cause such odd chemistry? Scientists immediately began proposing natural mechanisms. One intriguing possibility involves metal carbonyl compounds. These are molecules where metal atoms bond with carbon monoxide groups. Nickel tetracarbonyl, with the formula NiCO4, is a real chemical that forms under certain conditions. Iron pentacarbonyl, FeCO5, is its iron analogue. Both are volatile, meaning they can sublimate at relatively low temperatures compared to pure metals. If 3I-ATLAS somehow contained these compounds, their breakdown could release nickel and iron atoms along with carbon monoxide. The problem is that forming these compounds requires specific conditions, and maintaining them over the billions of years this object has spent in interstellar space is challenging. Metal carbonyls are not particularly stable. They decompose when exposed to ultraviolet radiation, which is abundant in space. They require cold, reducing environments to form in the first place. Could 3I-ATLAS have formed in some exotic stellar environment where these compounds were common? Perhaps around a carbon-rich star or in a molecular cloud with unusual chemistry. It's possible, but it's speculative, and that still doesn't fully explain the nickel-to-iron ratio. Even if metal carbonyls are involved, why would nickel carbonyls sublimate preferentially over iron carbonyls? The sublimation temperatures are different, but not dramatically so. You'd need a very specific thermal environment in the nucleus to drive nickel out while keeping iron locked away. And then, as the comet gets closer to the Sun and temperatures rise, iron should start appearing, which it does, according to some observations. Researchers noted that iron emission became detectable only when 3I-ATLAS crossed inside about 2.64 astronomical units from the Sun. That's consistent with a temperature-dependent release mechanism, but it requires a very specific layering or composition gradient in the nucleus. Some researchers, probably over late-night coffee in observatory break rooms, began whispering more exotic possibilities. What if some part of this object isn't natural? What if we're looking at materials that were processed or engineered? Nickel alloys are ubiquitous in human technology. Stainless steel, superalloys for turbines, corrosion-resistant coatings all use nickel. Nickel cyanide chemistry is used in electroplating. If you wanted to build a spacecraft or probe designed to survive interstellar travel, you might use nickel-rich alloys for their strength and resistance to corrosion. This is where we have to be very, very careful. The leap from unusual chemistry to alien artifact is enormous and requires extraordinary evidence. We have unusual chemistry. We do not have extraordinary evidence, but the question lingers, uncomfortable and tantalizing, in the back of every presentation and paper. If this chemistry is natural, it's teaching us that our models of comet formation are incomplete. If it's not natural, well, then we're having a very different conversation. The composition anomalies don't exist in isolation. They're part of a larger pattern, a web of strangeness that includes the sunward jet, unusual activity patterns, and other oddities we're only beginning to catalogue. When you start stacking anomalies, when you accumulate enough things that don't quite fit, you reach a tipping point where dismissing each one individually becomes harder than confronting them as a collective puzzle. And speaking of patterns, there's one more aspect of 3I-ATLAS's behaviour that defies easy explanation. This object doesn't just emit gas randomly, it pulses. Part 4. The 4-hour pulse. The object doesn't just spit gas into space in the gradual, continuous way we expect from sublimating ice. It does so like clockwork. Observers monitoring 3I-ATLAS detected periodicities in its brightness and outgassing activity, rhythmic variations that repeat roughly every 4 hours. Some data hints at a 2-hour period as well, possibly harmonically related. Picture a heartbeat. a regular pulse that speaks of some underlying mechanism driving activity on and off, with mechanical precision. In nature, regular periodicities usually arise from rotation. The most straightforward explanation for a comet showing a 4-hour activity cycle is that its nucleus spins with a 4-hour rotation period, and active regions on its surface come in and out of sunlight as it turns. This is not unprecedented. Many comet nuclei are elongated, irregular chunks of ice and rock that tumble through space. If jets are concentrated in certain areas, perhaps where volatile-rich deposits are exposed or where the surface structure funnels gas preferentially, then as the nucleus rotates, those jets turn on and off relative to our line of sight or relative to solar illumination. This is a perfectly reasonable, perfectly natural explanation. Comets with periodic outbursts are known. The rotation explanation makes sense, and if that's all that's happening here, then the 4-hour pulse is interesting but not paradigm-shattering. It tells us something about the shape and activity distribution of the nucleus, adds to our understanding of this particular object, but doesn't challenge fundamental physics. But let's dig a little deeper into what that explanation requires. For rotation to produce a clean, regular 4-hour signal in brightness and gas production, you need a very consistent active region, or a very specific geometry. Small irregularities in the nucleus shape, uneven heating, changes in the subsurface ice distribution as volatiles deplete, all of these should introduce noise and variation, yet the observations suggest a remarkably stable periodicity. That's not impossible, but it's noteworthy. It suggests either that the nucleus is surprisingly homogeneous in its activity pattern, or that whatever's driving the outburst is self-regulating in some way. Another natural possibility involves a binary nucleus, 2 chunks of ice orbiting each other. If the orbital period is 4 hours, tidal forces and mutual heating could drive periodic variations in activity. Binary comets and asteroids exist. We've observed them. The physics is well understood. If 3I-ATLAS is a contact binary or a separated binary, that could explain the periodicity without invoking anything exotic. But again, you'd need a fairly specific configuration, and we don't have direct imaging of the nucleus to confirm or rule this out. The object is too far away and too faint for even our best telescopes to resolve its nucleus directly. There's also the question of observational bias. Periodicities can be artifacts of how we sample data. If telescopes observe at regular intervals due to scheduling constraints or Earth's rotation, they might impose a false periodicity on noisy data. Astronomers know this and try to correct for it using statistical techniques. But it's always a concern. Could the 4-hour period be real in the data, but not real in the comet? Possibly. The fact that multiple independent observing campaigns seem to see consistent timing argues against pure artifact, but we should remain cautious. Now let's entertain the speculative side, the interpretations that push beyond standard comet physics. If the 4-hour pulse is real, and not simply explained by rotation or binarity, what else could cause it? Could there be some internal mechanism, some reservoir of volatiles being periodically released through a controlled vent? In a natural comet, internal pressure builds as ice sublimates below the surface, and eventually it breaches through weak points, creating outbursts. But those outbursts are usually chaotic, irregular, driven by fractures and collapses that don't follow neat schedules. A regular, sustained 4-hour cycle suggests either an extraordinary coincidence of natural factors or something more organised. Imagine if the nucleus had internal structure, chambers or pockets, where gas accumulates and then releases when pressure reaches a threshold. If those chambers were similar in size and the sublimation rate was steady, you might get periodic releases. It's like a geyser, where groundwater heating follows a predictable cycle based on reservoir size and heat input. But comets aren't geysers. They don't have stable underground cavities and regulated heat sources. They're rubble piles of ice and rock, porous and crumbly, not plumbed systems with valves and chambers. Unless, and here's where we veer into speculative territory, the object has some engineered component. If part of the structure includes materials or design elements meant to regulate gas release, you could imagine a periodic cycle driven by intentional mechanisms, vents that open and close, reservoirs that fill and empty, systems designed to maintain pressure or ration volatiles for long-duration travel. This sounds like science fiction because it is science fiction, at least until we have evidence to support it. But the 4-hour pulse, combined with the sunward jet and the nickel-dominated chemistry, stacks another anomaly onto the pile. There's one more angle to consider. If metal carbonyl compounds are involved in the outgassing, and if their formation or breakdown follows a cyclic chemical process, that could introduce periodicity. Imagine a feedback loop where heating drives sublimation. Sublimation cools the surface. Cooling allows carbonyls to recondense, and the cycle repeats. It's thermodynamically plausible if you have the right conditions, but again, this requires very specific chemistry and very stable conditions across the nucleus. It's not the first explanation you'd reach for, but it's not impossible. The 4-hour pulse matters because it's another data point that doesn't comfortably fit standard models. Taken alone, it's intriguing but explainable. Taken with everything else, it amplifies the sense that 3I-ATLAS is playing by different rules, and we're about to find out whether those rules apply only to this object, or hint at a broader category of interstellar visitors we've barely begun to understand. Because here's the urgent reality. We're not going to study this object leisurely over decades. We have one chance, one narrow window, to get close-up data from spacecraft that happen to be in the right place at the right time. That window is opening right now, and within days, instruments aboard 2 missions will sweep through nearby space, with their sensors pointed at this enigma. What they find, or fail to find, will shape our interpretation for years to come. Part 5. The clock is ticking. This may be our only chance to see it up close. In the vast emptiness of space, encounters between human-made spacecraft and celestial objects are rare, precious opportunities orchestrated by decades of planning or seized by fortunate timing. 3I-ATLAS arrived in our solar system unannounced, following an orbit we didn't predict, visible only after it rounded the Sun and began its outbound journey. We can't send a mission to rendezvous with it. There's no time to design, build, and launch a probe that could catch up to an object already accelerating back toward interstellar space. But through a stroke of cosmic luck, 2 spacecraft launched for entirely different missions will pass within detectable range during the critical period when the comet is still observable. The European Space Agency's Hera mission, designed to study the aftermath of NASA's DART impact on the asteroid Dimorphos, has a flyby window between October 25th and November 1st, 2025. During this period, Hera will pass within roughly 8 million kilometres of 3I-ATLAS. That's not close by spacecraft standards, not a true flyby in the sense of skimming past at close range, but it's close enough for certain instruments to gather valuable data. Hera carries cameras, spectrometers, and particle detectors designed to study asteroid surfaces and dust environments. Those same instruments can be retargeted, at least partially, to observe the comet's coma and tail structure. NASA's Europa Clipper, en route to Jupiter's ice-covered moon, has a similar opportunity between October 30th and November 6th. Again, we're talking millions of kilometres, not hundreds or thousands. Europa Clipper won't resolve the nucleus. It won't take close-up images showing surface details, but its spectrometers can analyse the light passing through the coma. Its plasma instruments can detect charged particles stripped from the comet by the solar wind. Its magnetometers might pick up signatures of magnetic draping, where the interplanetary magnetic field bends around the comet's ionized gas cloud. What makes these flybys particularly valuable is the diversity of measurements they can provide. Optical imaging from Earth captures the large-scale structure, the jets and coma morphology, but can't easily distinguish between different chemical species or measure the physical properties of dust grains. Spectroscopy from ground-based telescopes gives us composition, but with limitations imposed by Earth's atmosphere and the comet's brightness. Spacecraft instruments, even at significant distances, can access wavelengths blocked by our atmosphere, measure particles directly, and observe without the blurring and scattering that plague ground-based observations. If either Hera or Europa Clipper detects strong nickel emission, that would independently confirm the spectroscopic oddity seen from Earth. If they map the coma's structure and find asymmetries consistent with the sunward jet, that strengthens the case for a real physical feature rather than a processing artifact. If plasma detectors pick up unusual ion compositions or unexpected particle populations, that could hint at exotic chemistry or even non-natural materials outgassing from the nucleus. Conversely, if the spacecraft see nothing unusual, if their data shows a comet that looks chemically and physically normal, then we'd have to reconsider whether the ground-based anomalies are misinterpretations or measurement errors. There's a predicted opportunity that excites plasma physicists in particular. The comet's ion tail, that stream of charged particles stripped away by the solar wind, will cross paths with one or both spacecraft. When that happens, instruments designed to measure the local space environment will suddenly find themselves immersed in comet-derived plasma. They'll detect ions of whatever molecules are being ionized in the coma. Water ions, carbon monoxide ions, carbon dioxide ions, and yes, metal ions like nickel and iron if they're present in sufficient quantities. The mass spectrometers aboard these missions can distinguish between different ions based on their mass-to-charge ratios, giving us a direct measurement of what's actually in the tail, not just what we infer from spectroscopy. Magnetic field measurements offer another diagnostic. When the solar wind encounters a comet, the interplanetary magnetic field gets draped around the obstacle, creating a characteristic pattern. The shape and strength of this draping depend on the comet's outgassing rate, the composition of the coma, and how efficiently ions are created and interact with the field. Deviations from the expected pattern could indicate unusual plasma physics or unexpected conductivity, which in turn might point to exotic chemistry or material properties. But let's be realistic about the limitations. These spacecraft are not conducting dedicated comet flybys. They're on tight schedules with primary mission objectives that don't involve 3I-ATLAS. Hera needs to reach Dimorphos and carry out its survey. Europa Clipper needs to conserve power and momentum for its arrival at Jupiter. Pointing instruments at the comet requires fuel for attitude adjustments, competes with other observations, and risks missing planned activities. The distances involved mean resolution will be limited. We're not going to get detailed surface maps or close-ups of active vents. We're getting contextual data, compositional hints, and environmental measurements. There's also the timing challenge. The flybys happen over spans of days, and the comet is moving, changing, potentially varying in activity due to that 4-hour pulse or other factors. Coordinating observations, ensuring instruments are pointed correctly, and capturing data at optimal times requires careful planning and a bit of luck. Mission planners are doing their best, but they're working with constraints and uncertainties. Historically, opportunities like this have been hit or miss. When Oumuamua, the first confirmed interstellar object, tumbled through our solar system in 2017, we had no spacecraft in position to observe it closely. Everything we know came from telescopes on Earth and in Earth orbit, and it wasn't enough to definitively resolve the debates about its nature. By the time we realized how strange it was, it had already passed perihelion and was fading from view. We didn't get a second chance. Comet Borisov, the second confirmed interstellar visitor, arrived in 2019 and gave us more time to study it, but again, no spacecraft encounters, just remote observations. 3I-ATLAS is our third confirmed interstellar object, and for the first time, we have spacecraft close enough to potentially add in situ measurements to the remote observations. It's not the comprehensive mission we'd design if we had years to prepare, but it's infinitely better than nothing. What Hera and Europa Clipper detect or fail to detect will be cited in papers for years. It will inform models, settle or intensify debates, and guide how we interpret future interstellar visitors. The next few days will tell us whether the anomalies are robust and reproducible across different measurement techniques. If the spacecraft data aligns with the ground-based oddities, confidence in the reality of those oddities will skyrocket. If the spacecraft data contradicts or fails to see what telescopes have reported, then we'll have a calibration problem or a modelling issue to resolve. Either outcome is scientifically valuable. Either outcome moves us closer to understanding what 3I-ATLAS actually is. But while we wait for those flyby results, there's more to the story than just this one object. The anomalies don't stop at the sunward jet or the nickel chemistry or the rhythmic pulse. When you start cataloguing everything strange about 3I-ATLAS, when you line up all the observations that don't quite fit, you realise this object is an embarrassment of riches for anomaly hunters. It's not just one or two oddities, it's 15, maybe more, each demanding explanation, each adding weight to the sense that we're missing something fundamental. Part 6. 15. Anomalies and Counting. Let's assemble the dossier. Imagine we're building a forensic file, compiling every piece of evidence that makes 3I-ATLAS unusual compared to what we expect from a typical comet. Some of these anomalies might have natural explanations when considered individually. Some might be observational quirks or measurement uncertainties. But taken together, they paint a picture of an object that refuses to conform to our models. Anomaly 1 is the absence of a long sweeping tail. Most comets, especially when active and relatively close to the Sun, sport prominent tails stretching millions of kilometres. Dust tails curve gently, following the comet's orbit. Ion tails stream straight back, pushed by the solar wind. 3I-ATLAS has a coma, yes, but the tail structures are muted, shorter, less dramatic than you'd predict based on its brightness and activity level. It's as if the material leaving the nucleus isn't being efficiently swept into a tail, or the production rate is lower than the coma brightness suggests. Anomaly 2 is the sunward jet we've already discussed in detail. Material streaming toward the Sun, in defiance of radiation pressure and solar wind, represents a fundamental violation of standard cometary behaviour. This alone would make the object noteworthy. Anomaly 3 is the high nickel to low iron ratio, also covered earlier. Extreme metal abundance ratios don't fit solar or interstellar composition norms without invoking exotic formation environments or unusual chemistry. Anomaly 4 is the carbon dioxide-dominated coma. Most comets are water-rich. 3I-ATLAS flips that script, with CO2 outweighing water by a factor of 8. This suggests formation in a cold, carbon-rich environment, possibly around a different type of star or in a molecular cloud, with chemistry distinct from our solar system's birthplace. Anomaly 5 is the suppressed water relative to carbon dioxide. This isn't just restating Anomaly 4, it's highlighting that water, usually the dominant ice in comets, seems unusually depleted or locked away in this object. That has implications for where and how it formed and what its thermal history has been. Anomaly 6 is the rhythmic periodic outbursts, the 4-hour and possibly 2-hour cycles we discussed. Regular activity patterns hint at organised internal structure or specific geometric effects tied to rotation. Anomaly 7 is the asymmetric coma. Cometary comae are often asymmetric to some degree, but 3I-ATLAS shows pronounced asymmetries that don't align neatly with the expected dust and gas distribution models. The sunward jet contributes to this, but even accounting for that, the overall coma shape is odd. Anomaly 8 involves non-random orientation changes. Some observers reported that the direction of plumes or jets shifted over time in ways that didn't obviously correlate with orbital mechanics or expected rotation effects. This is a subtler anomaly, harder to pin down, but it adds to the sense that the object's activity isn't following a simple script. Anomaly 9 is the extreme negative polarization signature. Polarimetry measures how light from an object is polarized, and comets typically show certain polarization characteristics based on their dust properties. 3I-ATLAS exhibited a deep negative polarization branch, meaning at certain scattering angles, the light was polarized in a direction opposite to what's typical. This suggests unusual dust grain properties, perhaps a different size distribution, composition, or shape than solar system comets. Anomaly 10 is the anti-tail or narrow jet extension toward the Sun seen in earlier Hubble images. Before the dramatic TD image, Hubble captured hints of a narrow structure pointing sunward. At the time, it might have been dismissed as noise or a faint dust trail. In hindsight, it looks like an early warning of Anomaly 2. Anomaly 11 is the early water and hydroxyl outgassing far from the Sun. Observers detected water and OH emissions when the comet was still several astronomical units out, farther than you'd typically expect significant water ice sublimation. This fire hose of early activity suggests either that the surface ice is unusually exposed and volatile rich, or that some heat source beyond simple solar irradiation is driving sublimation. Anomaly 12 is the green colour shift during a lunar eclipse. Comets can appear greenish due to emission from carbon-bearing molecules like C2. But 3I-ATLAS showed a green hue, even though spectroscopy indicated low C2 abundance. The colour shift happened during a lunar eclipse when Earth's shadow affected the comet's illumination geometry, suggesting something about the scattering or emission properties changed in unexpected ways. Anomaly 13 is the detection of hydrogen cyanide emission. HCN was detected at a heliocentric distance of about 2.13 astronomical units. Interestingly, the HCN to CN ratio was similar to solar system comets, suggesting that at least some chemistry is normal. But the presence of cyanide compounds adds another layer to the already complex chemical inventory, especially when you consider how nickel cyanide chemistry is used in industrial processes here on Earth. Anomaly 14 is the rapid change of the nickel to iron ratio with heliocentric distance. iron emission appeared only when the comet crossed inside about 2.64 astronomical units from the Sun. Before that threshold, nickel dominated without significant iron. After crossing it, iron became detectable. This temperature-dependent release pattern suggests layered composition or distinct volatile reservoirs sublimating at different thresholds, but the sharpness of the transition is unusual. Anomaly 15 involves the delayed or withheld release of imagery from Mars orbiters. 3I-ATLAS passed relatively close to Mars, about 29 million kilometres, around October 3rd. Spacecraft like the ExoMars Trace Gas Orbiter and Mars Express have imaging capabilities that could have captured the comet. Yet public release of such imagery has been slow or absent. The high-resolution imaging science experiment HiRISE aboard NASA's Mars Reconnaissance Orbiter could have imaged the comet as well. The delay might be purely bureaucratic, a matter of data processing time or mission priorities. But it adds to the atmosphere of mystery, the sense that perhaps something in those images is being carefully reviewed before release. Each of these anomalies, considered in isolation, might be explained away. Unusual dust properties, exotic formation environment, observational artifacts, data processing delays. But when you stack 15 anomalies, when you see pattern after pattern that doesn't fit, you start to wonder whether the standard comet model is simply inadequate for interstellar visitors. Maybe objects formed around other stars, bathed in different radiation environments, composed of ices and dusts with different primordial chemistry, just behave differently. Maybe the rules we've derived from studying comets born in our own solar system don't apply cleanly to travellers from the galaxy at large. Or maybe, just maybe, we're looking at something that isn't entirely natural. That's the whisper in the back of the room, the speculation that no one wants to voice too loudly because it sounds like fringe science or tabloid fodder. But the whisper persists because the data keeps piling up in uncomfortable ways. Nickel without iron, cyanide compounds, rhythmic pulses, sunward jets. It's not that any single one of these screams artificial, it's that together they form a constellation of oddities that makes you question assumptions. So let's entertain that speculation directly, not as a conclusion, but as a thought experiment. What if some component of 3I-ATLAS, whether a coating, a structural element, or a deliberate payload, involves engineered materials? What would we expect to see, and does it match what we're observing? Part 7. Engineered Alloy Hypothesis. One of the wildest hypotheses circulating in the margins of the scientific discussion is this. Parts of 3I-ATLAS may be engineered, not the entire object necessarily. Perhaps just a shell, a layer, a component embedded within or attached to what is otherwise a natural comet nucleus. This idea sounds like science fiction, and it probably is, but let's follow the logic and see where it leads. Human technology makes extensive use of nickel alloys. Stainless steel, the ubiquitous corrosion-resistant metal found in everything from kitchen sinks to spacecraft components, contains chromium and nickel. Superalloys used in jet engines and rocket nozzles, materials that must withstand extreme temperatures and corrosive environments, are often nickel-based. Inconel, Hastelloy. These are trade names for nickel alloys prized for their strength and durability. If an advanced civilization wanted to build a probe or instrument package designed to survive millions of years drifting through interstellar space, exposed to cosmic rays, micrometeor impacts, and the corrosive effects of trace gases, nickel alloys would be a reasonable choice. Nickel cyanide chemistry is used in electroplating, a process where a thin layer of nickel is deposited onto another metal for protection or aesthetic purposes. The chemistry involves cyanide ions, which bind to nickel and help control the deposition process. If you were coating a structure with nickel for durability, you'd be working with nickel cyanide baths. Over time, especially under the harsh conditions of space, such coatings might degrade. Ultraviolet radiation, thermal cycling, micrometeorite abrasion, all of these could slowly ablate a nickel-rich surface layer. As that layer breaks down, it would release nickel atoms and potentially cyanide compounds into the surrounding space. Now imagine this hypothetical nickel-coated structure embedded in or attached to a comet nucleus. As the comet approaches the sun and heats up, the surrounding ice sublimates, releasing gas and dust. The structure, if it's partially exposed, also heats up. Any remaining volatile compounds, any degraded surface materials begin to outgas. You'd see emissions of nickel, possibly cyanide species, and depending on the detailed chemistry, various carbon-bearing molecules. The ratios wouldn't match normal cometary material because you're not just seeing sublimated ice. You're seeing the breakdown products of engineered materials mixed in with the natural outgassing. This scenario could explain the high nickel to iron ratio if the engineered component used a nickel-rich alloy with minimal iron. It could explain the hydrogen cyanide detections if cyanide chemistry was involved in the material's production or surface treatment. It could even explain the carbon dioxide dominance if the structure included carbon-based components, polymers, or organic coatings that break down into CO2 under ultraviolet irradiation and heating. The rhythmic 4-hour pulse might make more sense in this context too. If the engineered component has vents, valves, or structural features that regulate gas flow, either by design or as a consequence of how it's degrading, you could get periodic releases. Imagine a compartment that fills with sublimated gas from surrounding ice, builds pressure, and then vents through a crack or opening. Once vented, the pressure drops, the filling process starts again, and the cycle repeats. 4 hours would be the characteristic timescale for this particular system, determined by the size of the compartment, the sublimation rate, and the flow resistance of the vent. The sunward jet becomes less mysterious if it's driven by something other than random sublimation. Suppose the engineered structure has a directional vent, a nozzle or opening that happens to point sunward based on how the object is tumbling or oriented. Gas escaping through that vent would create a jet in that direction regardless of where the sun is. It wouldn't be fighting radiation pressure so much as bypassing the usual mechanisms by releasing from a specific point with enough force to overcome solar wind effects locally. This all sounds disturbingly plausible once you start down the path. But we have to be brutally honest about what this hypothesis requires. It requires that an advanced civilization built a probe or object, that this object ended up in interstellar space, that it happened to pass through our solar system, and that it just happens to have undergone enough degradation to release detectable signatures without being obviously artificial in structure. That's a lot of coincidences. It also requires that we're misinterpreting or overlooking natural explanations that could account for the same observations. The scientific community has a term for this kind of speculation. It's called the extraordinary claims require extraordinary evidence principle, often attributed to Carl Sagan. The idea is simple. The more unusual and paradigm-shifting a claim is, the higher the burden of proof. Claiming that 3I-ATLAS has unusual chemistry is a modest claim requiring modest evidence. Claiming it's partially artificial is an extraordinary claim requiring extraordinary evidence. Do we have that level of evidence? No. We have intriguing anomalies, suggestive patterns, and a lack of fully satisfying natural explanations. That's not the same as proof of artificiality. Natural mechanisms can surprise us. The universe is creative. Chemistry under exotic conditions can produce unexpected results. Interstellar environments are not well sampled. We've studied solar system comets extensively, but those comets all formed in the same protoplanetary disk from the same starting. Materials under similar conditions. An interstellar comet formed around a different star, in a molecular cloud with different metallicity, irradiated by a different spectrum of starlight, might just be weird without being artificial. It might teach us that normal comet chemistry is more diverse than we thought. But let's not dismiss the speculation entirely. Science advances by considering possibilities, testing them, and either confirming or ruling them out. The engineered alloy hypothesis is testable, at least in principle. If the spacecraft flybys detect particles or ions with isotopic ratios inconsistent with natural nucleosynthesis, that would be a smoking gun. If imaging reveals geometric structures, straight edges, or regular patterns that don't occur in natural rubble piles, that would be compelling. If spectroscopy finds molecules that only exist in industrial processes and have no plausible natural formation pathway, we'd have to take the idea seriously. Conversely, if future observations find natural mechanisms that explain the nickel dominance, the carbon dioxide excess, and the sunward jet without invoking engineered materials, then the hypothesis collapses under Occam's razor. The simpler explanation wins. We're not there yet. We're in the uncomfortable in-between zone where the data is weird enough to make you think, but not definitive enough to conclude. What makes this moment particularly fascinating is that we're not just speculating in a vacuum. We're on the verge of getting new data. The flyby results will either strengthen or weaken the case for exotic explanations. But even as we wait for that data, there's another layer to this story, another angle that makes the mystery deeper. Sometimes what you don't see is as important as what you do see, and in the case of 3I-ATLAS, there are missing pieces, withheld images, and unexplained delays that add an uncomfortable layer of intrigue. Part 8. Missing Data and the Mars Orbiter. Silence. Sometimes what's hidden speaks as loud as what's shown. In the age of instant information, where astronomical discoveries are tweeted within hours, and preprint servers overflow with fresh papers, the absence of expected data becomes its own kind of signal. 3I-ATLAS passed relatively near Mars in early October, close enough that multiple Mars orbiters should have had excellent views of the comet. Yet the public release of imagery from those orbiters has been conspicuously slow, and in some cases apparently absent. The ExoMars Trace Gas Orbiter, a European Space Agency mission designed to study the Martian atmosphere, carries cameras capable of imaging objects in space. Mars Express, another ESA orbiter that's been circling Mars since 2003, has imaging capabilities as well. NASA's Mars Reconnaissance Orbiter hosts the high-resolution imaging science experiment, HiRISE, a camera so powerful it can resolve features less than a meter across on the Martian surface. When pointed at a comet millions of kilometers away, HiRISE wouldn't achieve surface-level resolution, but it could certainly capture the coma structure, jet features, and overall morphology with far better clarity than most ground-based telescopes. 3I-ATLAS reached its closest approach to Mars around October 3rd at a distance of roughly 29 million kilometers. That's not a close flyby by any means, but it's well within imaging range for spacecraft instruments. The opportunity was there. The question is whether those instruments were actually pointed at the comet, and if they were, why haven't we seen the results? There are perfectly mundane explanations for delayed data release. Spacecraft data goes through processing pipelines. Raw images need calibration, correction for instrument artifacts, and validation before being released to the public, or even to the broader scientific community. Mission teams have priorities. Mars orbiters are there to study Mars, not to conduct opportunistic comet observations. Taking time away from primary mission objectives to image a passing comet requires justification, scheduling, and sometimes negotiation between different science teams. It's possible that the observations were low priority, done if convenient but not essential, and the data simply hasn't been processed yet because other tasks took precedence. There's also the reality of observing geometry. Just because a comet passes near Mars doesn't guarantee that orbiters in Martian orbit can easily point at it. Orbital mechanics, communication windows with Earth, spacecraft orientation constraints, all of these factors limit what's actually feasible. Perhaps the Mars orbiters weren't in the right position, or weren't configured to observe the comet effectively. Perhaps they tried but encountered technical issues or weather, well, not weather in the Earth sense, but dust storms on Mars can affect surface-based observations, though they wouldn't affect spacecraft cameras in orbit. But let's consider the less mundane possibilities. What if the images exist, have been processed, and are being withheld pending further analysis? What if something in those images is unusual enough that mission teams want to triple-check their interpretations before releasing potentially controversial data? Space agencies are cautious institutions. They've been burned before by releasing data that was later reinterpreted or corrected, leading to public embarrassment and erosion of trust. If HiRISE or TGO captured something unexpected in the inner coma of 3I-ATLAS, something that doesn't fit standard models, the instinct would be to verify thoroughly before publication. There's historical precedent for this kind of caution. When unusual features are detected, when anomalies appear that might challenge established science or generate sensational headlines, the data undergoes extra scrutiny. Review boards convene. Alternative explanations are exhaustively explored. Only when the team is confident that they understand what they're seeing, or confident that they don't understand but have exhausted prosaic explanations, does the data get released. This process can take months or even years. The delay could also be political or bureaucratic rather than scientific. Space agencies are government or intergovernmental entities subject to public relations considerations, funding pressures, and international cooperation agreements. If data from one mission impacts the interpretation of another mission, or touches on sensitive topics, there might be coordination delays while different stakeholders align their messaging. This sounds cynical, and perhaps it is, but these organizations don't operate in a vacuum. They navigate complex landscapes of public perception, scientific integrity, and institutional interests. Some observers have speculated, perhaps unfairly, that if the Mars orbiter images showed clear evidence of artificial structure or unambiguous anomalies that would force a rethink of what 3I-ATLAS is, those images might be subject to deliberate withholding. The reasoning goes that extraordinary claims require extraordinary caution, and releasing such images prematurely could trigger a cascade of media hype, public confusion, and pressure on scientists to provide answers they don't yet have. Better to withhold until a fuller picture emerges, until multiple lines of evidence converge and a coherent narrative can be presented. This kind of speculation quickly slides into conspiracy theory territory, and we should be careful not to go there without evidence. There's no indication of a coordinated cover-up. There's no leaked memo or whistleblower suggesting that something astonishing is being hidden. What we have is an absence of expected data and a natural human tendency to fill information voids with speculation. The absence might mean nothing. It might mean everything. We don't know yet. What makes this absence frustrating is that the Mars orbiter imagery could answer key questions. If the images show a perfectly normal-looking coma with no sunward jet or unusual features, that would cast doubt on the ground-based observations. If they show the sunward jet clearly, from a different angle and with high resolution, that would confirm it beyond reasonable doubt. If they show structure in the inner coma, hints of asymmetry or focused venting, that would guide our models. The data exists presumably in some form. We're just waiting for it to emerge from the institutional machinery. But missing Mars imagery isn't the only odd coincidence swirling around 3I-ATLAS. In the days surrounding the comet's perihelion and its most unusual behaviour, other strange events were reported in the near-Earth and solar environment. Taken together, they form a pattern that might be pure coincidence or might hint at something more coordinated or causally connected, happening in our cosmic neighbourhood. Part 9. Cosmic Coincidences and Sun-Diving Objects. What if 3I-ATLAS's oddities aren't isolated? What if they're part of a pattern? Between October 11th and October 14th, 2025, reports emerged of 4 distinct sun-grazing objects diving toward the Sun. These objects, tracked by solar observatories, appeared to originate from roughly the same general direction in the sky as 3I-ATLAS. They plunged toward our star, some apparently disintegrating, others vanishing into the solar glare. Sun-grazing comets are not rare. The Kreutz family, a group of comets thought to be fragments of a larger progenitor that broke apart centuries ago, regularly sends members diving sunward. Solar observatories catalogue dozens of these doomed comets every year as they vaporize in the sun's intense heat. But the timing here is curious. 4 objects in 4 days, all from a similar direction, overlapping with the period when 3I-ATLAS was exhibiting its most unusual behaviour and approaching its own perihelion. Coincidence? Probably. The sky is big, and the volume of space near the Sun is constantly being crossed by small bodies. Our improved observational capabilities, especially with space-based solar telescopes, mean we're detecting more of these objects than ever before. Finding 4 in quick succession isn't statistically impossible, or even particularly unlikely during active periods, yet the clustering nags at the imagination. Could these sundivers be related to 3I-ATLAS? Could they be fragments that broke off earlier in its trajectory, following slightly different orbits that converged on the Sun around the same time? Cometary nuclei are fragile. Tidal forces, thermal stresses, and rotational instability can shatter them into multiple pieces. If 3I-ATLAS shed fragments months or years ago, those fragments might have orbits differing slightly from the main nucleus, leading them to arrive at perihelion at different times. We've seen this with other comets. Shoemaker-Levy 9 famously fragmented before its collision with Jupiter, creating a string of pearls that impacted over several days. Spectroscopic analysis of the sun-diving objects could test this hypothesis. If their composition matches 3I-ATLAS's unusual chemistry, that would strengthen the connection. If they show normal cometary composition, they're probably unrelated. But obtaining detailed spectra of objects about to be incinerated by the Sun is challenging. They're faint, fast-moving, and visible only briefly. Most sun-grazing detections come from coronagraph images that block the Sun's disk to reveal the faint surroundings. Those images don't provide spectral information. Another odd event occurred during this period that caught public attention, though it's even harder to evaluate. During a SpaceX Starship launch, observers analysing video of the spacecraft against the backdrop of the moon noted a bright point of light near the lunar glare. This point appeared to hover for several seconds in a position that didn't correspond to any known satellite, star or planet. Then it disappeared. The internet predictably erupted with speculation. Was it a genuine object, a spacecraft, a piece of debris, or was it an optical artifact, a lens flare, a reflection within the camera optics? Lens flares are common in astrophotography, especially when bright objects like the moon are in the frame. Light can scatter within lenses, reflect off sensor surfaces, and create ghost images that appear as bright spots or streaks. Distinguishing between real objects and optical artifacts requires careful analysis of the original footage, understanding of the camera system, and ideally, confirmation from multiple independent cameras. In this case, such analysis has been inconclusive or absent from public reporting. The bright point might be something real, but it's just as likely, if not more likely, to be a mundane artifact. What makes this event tangentially relevant to 3I-ATLAS is the timing. The Starship launch occurred in mid-October, overlapping with the period of heightened comet activity and the sun diving objects. If you're inclined toward pattern seeking, you might wonder whether there's a connection. Could the bright point near the moon be related to whatever's causing the comet anomalies? Could there be some coordinated activity, some hidden phenomenon affecting multiple objects in near-Earth space simultaneously? This is where we have to pump the brakes on speculation. Coincidences happen. Humans are pattern recognition machines, evolved to spot connections even when none exist because false positives were less costly than false negatives in our ancestral environment. Seeing unrelated events and constructing narratives linking them is something our brains do automatically. It doesn't mean the connections are real. But let's entertain the idea for a moment, not as a serious hypothesis but as a thought experiment. Suppose there was some cosmic event or pulse, some disruption in the interplanetary environment that affected multiple small bodies simultaneously. Perhaps a burst of high-energy particles from the sun, a coronal mass ejection with unusual properties, or a density wave in the interplanetary medium. Could such an event trigger outgassing in comets, destabilize orbits, or interact with dust and debris in ways that produce transient optical phenomena? The physics would be challenging to work out, but it's not impossible in principle. Coronal mass ejections are massive eruptions of plasma and magnetic field from the sun that travel through the solar system at high speed. When they impact Earth, they cause geomagnetic storms, auroras, and disruptions to satellites and power grids. When they encounter comets, they can compress the coma, intensify the ion tail, and trigger outbursts. If a particularly strong or unusual CME occurred in early to mid-October, it could have affected 3I-ATLAS and potentially other bodies in interplanetary space. Solar observatories monitor the sun constantly for such events. A quick check of solar activity reports for October would reveal whether any significant CMEs or solar flares occurred during the relevant period. If so, that could be a natural explanation linking some of the observations. If not, we're back to coincidence as the most likely explanation. These sun-diving objects, this starship bright point, and 3I-ATLAS's behaviour might simply be unrelated events that happen to cluster in time by chance, or they might be connected by some common cause we haven't identified. Without more data, we can't distinguish between these possibilities. What we can say is that October 2025 has been an unusually eventful month for near-Earth and solar system astronomy, and 3I-ATLAS sits at the centre of that activity, the most anomalous and intensely studied object in the mix. But 3I-ATLAS isn't the first interstellar visitor to challenge our assumptions. It's part of a progression, a series of objects arriving from beyond our solar system, each one breaking rules in its own way. To understand where 3I-ATLAS fits in the larger picture, we need to look back at its predecessors and ask whether there's a pattern emerging in how interstellar visitors behave. Part 10. The reversal motif in cosmic visitors. 3I-ATLAS may not be unique, but it may follow a pattern that's only now becoming visible. The pattern is one of reversal, of objects that arrive from interstellar space and proceed to violate our expectations in fundamental ways. It started in October 2017 with one I/Oumuamua, the first confirmed interstellar object detected passing through our solar system. Oumuamua was strange from the start. It showed no visible coma, no tail, no obvious signs of outgassing despite passing close enough to the sun, that any water ice should have sublimated vigorously. It was classified as an asteroid based on that lack of activity, but its trajectory told a different story. As astronomers tracked Oumuamua's path, they noticed it was accelerating slightly away from the Sun in a way that couldn't be explained by gravity alone. Something was pushing it. In comets, this kind of non-gravitational acceleration is common and well understood. Outgassing creates a rocket effect. Material jets off the sunward side, and the recoil nudges the nucleus in the opposite direction. But Oumuamua wasn't outgassing visibly. No coma, no jets, no detectable gas. Yet it accelerated as if it were. Explanations proliferated. Maybe it was outgassing something very faint, hydrogen perhaps, that wouldn't produce a visible coma but could still provide thrust. Maybe it was an unusually strong radiation pressure effect acting on a very thin, flat object, shaped like a solar sail. Maybe it was solid hydrogen ice, exotic and fragile, sublimating invisibly. Each explanation had problems, each required assumptions that stretched what we considered normal. And then there was the shape. Observations suggested Oumuamua was extremely elongated, perhaps 10 times longer than it was wide, cigar-shaped or maybe even pancake-flat. No asteroid or comet in our solar system looked quite like that. The scientific community debated intensely. Most researchers favoured natural explanations, exotic as they were. But a few, most prominently astronomer Avi Loeb from Harvard, suggested that Oumuamua's properties were consistent with artificial origin, perhaps a light sail or probe from an alien civilization. That suggestion was controversial, to put it mildly. Most astronomers found it premature and insufficiently supported by the data. But the idea entered public consciousness and refused to leave. Oumuamua became not just a scientific puzzle, but a cultural touchstone for the question of whether we're alone in the universe. Then, in August 2019, amateur astronomer Gennady Borisov discovered 2I-Borisov, the second confirmed interstellar object. This one looked much more like a normal comet. It had a clear coma, showed vigorous outgassing, contained familiar molecules like water and carbon monoxide in expected ratios. Its behaviour was comforting in its normalcy. See, researchers said, interstellar visitors can be ordinary. Borisov proved that not every object from beyond our solar system needs to break the rules. It was a comet. It acted like a comet, and while its interstellar origin was extraordinary, its nature was reassuringly familiar. But now we have 3I-ATLAS, and the strangeness is back with a vengeance. If Oumuamua was strange for what it didn't show, 3I-ATLAS is strange for what it does show in the wrong places. A sunward jet where there should be an anti-solar tail, nickel without iron, carbon dioxide drowning out water, rhythmic pulses like a mechanical heartbeat. This object isn't failing to behave like a comet, it's behaving like a comet that read the textbook backwards. When you line up these three visitors in chronological order, a pattern emerges. First, an object with no activity where there should be activity but mysterious acceleration. Second, an object with normal activity and reassuring chemistry. Third, an object with reversed activity and bizarre chemistry. It's as if the universe is testing us, presenting a progression of anomalies to see how we respond. Or perhaps it's teaching us that our category of comet, and asteroid, and interstellar visitor are too rigid, too based on a sample size of one solar system. The key question is whether these objects are outliers or harbingers. Are they rare exceptions, statistical flukes that grab our attention precisely because they're unusual, while hundreds of normal interstellar objects pass unnoticed because they're too faint or too ordinary to detect? Or are they the first representatives of a much larger population of weird things drifting through the galaxy, objects formed under conditions so different from our solar systems that they naturally violate our expectations? The answer has profound implications. If most interstellar visitors are strange, then our solar system's comets and asteroids might be the outliers, products of one particular set of formation conditions that aren't representative of the galaxy as a whole. We'd need to broaden our models, incorporate a much wider range of chemical and physical possibilities, and accept that what we call normal is just local normal, not universal normal. If most interstellar visitors are ordinary and we're just noticing the weird ones because they're noticeable, then Oumuamua and 3I-ATLAS are curiosities, interesting but not paradigm-shifting. They're the astronomical equivalent of two-headed calves, rare birth defects or unusual circumstances that don't reflect the broader population. We'd still want to understand them, but we wouldn't use them to rewrite our textbooks. The reversal motif, this tendency for interstellar objects to flip expectations, might be telling us something deeper about the galaxy's diversity. Star formation happens in a variety of environments. Some stars form in dense clusters, where radiation and gravitational interactions are intense. Some form in isolation in the sparse outer regions of molecular clouds. The composition of the gas and dust varies depending on the metallicity of the region, the history of previous supernovae enriching the material, and the presence of nearby massive stars. Comets forming around a star in a metal-rich region might have different chemistry than those forming in a metal-poor region. Comets forming close to massive stars might be irradiated more intensely, altering their surface properties or driving off certain volatiles preferentially. 3I-ATLAS, with its carbon dioxide dominance and metal anomalies, could be a product of such an exotic birthplace. Maybe it formed around a carbon star, a type of star where carbon is more abundant than oxygen in the outer atmosphere, leading to carbon-rich dust and chemistry. Maybe it spent time in a dense molecular cloud where cosmic rays processed the ices in unusual ways. Maybe it's old, billions of years old, and its surface has been altered by prolonged exposure to the interstellar radiation field. All of these are natural explanations that could account for oddities without invoking artificiality. But the reversal motif also resonates with a more speculative interpretation. If interstellar space is occasionally traversed by probes or artifacts from other civilizations, those objects would naturally violate our expectations because they weren't designed by natural processes. They'd have materials chosen for engineering reasons, not cosmic abundance. They'd have structures optimized for function, not random accretion. They'd potentially have systems that operate rhythmically or directionally because they were built to do so. In that framework, the reversal isn't a coincidence, it's a signature. Objects that break the rules might be breaking them because they were made by rule breakers. This brings us to a critical juncture. 3I-ATLAS, Oumuamua, and potentially future interstellar visitors are pushing us to expand our thinking. Whether the explanation is exotic natural processes or something more radical, we're being forced to confront the limits of our models, and as we grapple with these cosmic puzzles, it's worth noting that 2025 has been a year of paradigm-challenging discoveries across multiple fields of science. 3I-ATLAS isn't happening in isolation. It's happening in a year when other fundamental assumptions are being tested, when dark stars are confusing cosmologists, when AI is discovering patterns in physics that humans missed, when quantum teleportation is achieving milestones that seemed impossible decades ago, and when fusion energy is crossing thresholds that promise to reshape civilization. Maybe we're entering a period where anomalies are the norm, where the universe is revealing complexities we hadn't anticipated across every scale we study. Part 11. The Dark Stars Debate. Recent results from the James Webb Space Telescope and other surveys have thrown cosmology into an unexpected debate about the formation sequence of the universe's first structures. The standard model holds that galaxies formed first, growing from small density fluctuations in the early universe, and then black holes formed at their centres as matter accumulated and collapsed. This sequence made sense. Gas condenses into stars, stars cluster into galaxies, and eventually enough mass concentrates in galactic cores to form supermassive black holes. It's a bottom-up process, building complexity from simple beginnings. But JWST keeps finding black holes that seem too big, too early. Supermassive black holes, millions to billions of times the mass of our Sun, existing when the universe was less than 1 billion years old. That's not enough time for them to grow through the standard process of accretion and mergers. Either these black holes started much bigger than theory predicts, or they grew much faster, or the sequence is wrong. Maybe black holes formed first, before galaxies, seeding the structures that would later become galactic centres. This possibility has led to the concept of dark stars, hypothetical early objects powered not by nuclear fusion like normal stars, but by the annihilation of dark matter particles. If dark matter accumulated in dense clumps in the early universe and began annihilating, it could release energy that would heat surrounding gas and make it glow. These dark stars could be enormous, far larger than any fusion-powered star, and they could eventually collapse into black holes that would then serve as seeds for galaxy formation. It's a reversal of the expected order, black holes before galaxies instead of galaxies before black holes. The evidence isn't definitive yet. The observations pushing this debate are at the edge of JWST's capabilities, and alternative explanations exist. Maybe the black holes aren't as massive as they appear. Maybe they're accreting at higher rates than we thought possible. Maybe our models of early universe conditions need refinement. But the fact that we're even having this conversation, that the standard cosmological sequence is being questioned based on hard observational data, reflects a broader theme. Our models are being tested and found wanting. The universe is more complex, more surprising than our neat frameworks anticipated. If we can be wrong about something as fundamental as the formation sequence of galaxies and black holes, structures that define the large-scale architecture of the cosmos, then being wrong about the behaviour of interstellar comets seems almost trivial by comparison. Both cases involve taking what we learned from limited samples and assuming it applies universally, only to find that the universe has tricks we didn't account for. The dark stars debate matters for our discussion of 3I-ATLAS because it establishes context. We're not in an era of settled science where all the big questions are answered, and we're just filling in details. We're in an era where fundamental assumptions are being challenged across multiple domains. That doesn't mean every anomaly is revolutionary. Most anomalies turn out to be measurement errors, calibration issues, or previously known effects in unfamiliar guises. But some anomalies are real, and some of those real anomalies force us to rebuild our theories from the ground up. 3I-ATLAS might be one of those theory-breaking anomalies, or it might be a lesson in exotic but natural comet chemistry. The point is, we can't dismiss it just because it doesn't fit our models, because our models are demonstrably incomplete. The universe is under no obligation to conform to our expectations, and 2025 is teaching us that lesson repeatedly. Part 12, AI and Physics at the Crossroads. In 2025, artificial intelligence is no longer just assisting scientists, it's discovering things humans missed. Machine learning algorithms trained on vast datasets are identifying patterns, correlations, and anomalies that would take human researchers years to find, if they found them at all. This is transforming every field it touches, and astrophysics is no exception. Recent papers in high-energy physics and cosmology have listed AI systems as co-authors, acknowledging that the algorithms contributed substantively to the discovery process. These aren't just data processing tools, they're hypothesis generators, pattern recognizers operating in high-dimensional spaces where human intuition struggles. An AI trained on galaxy spectra can spot unusual emission lines in thousands of objects simultaneously. An AI analyzing light curves from variable stars can detect periodicities buried in noise that visual inspection would miss. This capability has profound implications for studying objects like 3I-ATLAS. The data we have, spectra, images, light curves, contains far more information than any single human researcher can fully extract. There are correlations between chemical abundances and activity patterns, subtle timing relationships, spatial structures in the coma that might reveal internal organization. An AI specifically trained on cometary data, and then turned loose on 3I-ATLAS might identify patterns that explain the anomalies, or flag additional oddities we haven't noticed. But this power comes with risks. AI systems can hallucinate patterns in noise. They can overfit to training data, learning the quirks of specific instruments rather than true physical relationships. They can encode biases present in their training sets, reinforcing assumptions rather than challenging them. An AI trained primarily on solar system comets might flag everything about 3I-ATLAS as anomalous, simply because it's different, not because it's physically impossible. The key is combining AI's pattern recognition with human skepticism and physical intuition. Let the AI scan for oddities, but demand that humans verify them, check for artifacts, and construct physical models to explain them. This hybrid approach is already being used in gravitational wave astronomy, where AI flags potential signals in detector noise and human experts evaluate whether they're real events or glitches. The same approach could revolutionize how we study interstellar visitors. Imagine an AI system that ingests every observation of 3I-ATLAS, every spectrum, every image, every timing measurement, and looks for correlations. It might discover that the 4-hour pulse correlates with specific spectral line strengths, suggesting a chemical cycle. It might find that the sunward jet's intensity varies with the nickel-to-iron ratio, hinting at a shared driving mechanism. It might identify precursor signals, subtle changes in the coma hours before outbursts, that could predict future activity. Or it might find nothing, confirming that the anomalies are genuinely random, or driven by processes too complex or chaotic for pattern recognition. That outcome would also be valuable. It would tell us we're not missing obvious connections, that the mystery is genuinely mysterious. The broader point is that 2025 represents a threshold in how we do science. We're augmenting human intelligence with machine intelligence in ways that are qualitatively different from previous computational tools. This changes what's possible, what questions we can ask, and how quickly we can answer them. If 3I-ATLAS is hiding secrets in its data, AI might be the key to unlocking them. And if AI confirms that the anomalies are robust and interconnected, that will make the case for exotic explanations, natural or otherwise, significantly stronger. Part 13. The Quantum Teleportation Milestone. Information does not travel. It dies in one place and resurrects in another, without ever crossing the space between. This sounds like magic, but in 2025 it is becoming routine. Researchers have just achieved something that would have seemed impossible a decade ago. They have successfully teleported quantum information across 56 kilometers of standard fiber optic cable, coexisting alongside ordinary internet traffic, the same cables that carry your emails and video streams. This is not theoretical, it happened. The breakthrough came from scientists at Northwestern University, working with teams across multiple institutions, and their results demonstrated that quantum states could be transferred with greater than 90% accuracy over metropolitan distances using equipment that integrates with existing infrastructure. Think about that for a moment. The same fibre that brings Netflix to your home, the same cables buried beneath city streets that carry banking transactions and medical records, are now carrying quantum information. Reality itself, in its most fundamental form, is being transmitted alongside your morning news. The mechanism behind this operates on principles that should trouble anyone who believes space is merely empty void. Quantum entanglement creates a link between two particles, a connection so instantaneous that Einstein himself called it spooky action at a distance. Two particles become entangled, their properties forever bound. You measure one, and instantaneously the other responds, no matter if they are separated by kilometers or light years. The physicists doing this work carefully prepare pairs of entangled photons. One photon carries the quantum state they want to transfer. The other is waiting at the destination. The moment they perform a measurement on the first photon and the intermediary particle, that measurement forces the distant photon to collapse into the state of the original. The information is gone here. It exists there. No signal travels between them. No message passes through space. The correlation is instantaneous. Einstein hated this. He called it ghostly, unacceptable, a violation of everything physics should be. Yet here we are in 2025 harnessing that ghostliness. But here is where it gets crucial for understanding the implications. This process requires timing so precise that error correction becomes a complex dance. Every entangled photon travels through fibre, and fibre is hostile to delicate quantum states. Thermal noise, vibrations, electromagnetic interference, all these threaten to decohere the quantum information before it arrives. The researchers solved this using advanced filtering techniques, superconducting detectors cooled to temperatures just above absolute zero, and active feed-forward protocols where classical information about measurement results travels alongside the quantum signal. The classical information tells the receiver how to manipulate the quantum state to restore it perfectly. It is like sending both a message and the key to decode it simultaneously, except the key itself is quantum and must be protected with extraordinary care. The distances involved are not vast by cosmic standards, but they are vast by the standards of quantum systems. 56 kilometers is an enormous distance to maintain quantum coherence. The fact that this is now repeatable, that it can be done over and over with consistent results, marks a transition from laboratory curiosity to practical technology. The implications for deep space communication are staggering. Imagine probes exploring the outer solar system or eventually interstellar space. Normal radio signals degrade over distance, require enormous power, travel at light speed, and take hours to cross the solar system. A transmission to Mars takes between 4 and 24 minutes depending on orbital positions. A message to the Voyager probes takes 18 hours to reach them. This is not because the signals are weak, but because light itself moves at a finite speed. A quantum communication link would establish a secure channel where any eavesdropping attempt instantly destroys the signal, alerting both parties to intrusion. The security is absolute. not through encryption but through the laws of physics themselves. More importantly, quantum communication could enable distributed quantum computing, where distant quantum processors collaborate on the same problem in real time without the lag that light speed imposes on classical communication. You cannot transmit faster than light, but quantum entanglement allows you to coordinate in ways that appear, to the observer, almost instantaneous. The universe grants us this gift, the ability to have particles separated by vast distances act as if they were one unified system. Here is where the analogy crystallizes. Imagine fiber optics as living blood vessels carrying information through space itself. Classical fiber optics carry pulses of light encoded with ones and zeros, binary information, the digital language of modern computing. Quantum fiber optics would carry something more fundamental, the raw quantum possibility itself, like the difference between describing a landscape and standing in it, like the difference between reading sheet music and hearing the symphony. The information is not a message about reality. It is reality transferred intact from one location to another. Now consider the comet 3I-ATLAS. What if, in the distant future, humanity sends quantum-equipped probes to intercept objects like this? These probes would need instantaneous coordination, secure, channels that cannot be intercepted, distributed processing power to analyze anomalies in real time. The mechanisms enabling that future technology are being tested today. We are building the infrastructure for cosmic communication networks without realizing it. This brings us to a darker speculation, one that connects the mechanics of quantum teleportation to the mysteries of 3I-ATLAS. If quantum communication becomes commonplace and enables advanced propulsion or exotic physics applications, could Atlas itself be using something similar? Not necessarily quantum teleportation as humans understand it, but a mechanism that exploits quantum phenomena to move matter or energy in unexpected ways. The rhythmic outbursts, the chemical composition that does not match models, the coherent jets that should not exist in a body so small and icy, all of these hint at something manipulating the physics at scales where quantum effects become significant. Stars are mostly classical, planets are classical. But small bodies, especially those with complex internal structure, ice and organics, they operate in a regime where quantum phenomena could genuinely matter. Quantum tunneling could allow particles to move through barriers they should not be able to cross. Quantum fluctuations could drive processes we do not yet understand. Entanglement between subsystems could create correlations that appear impossible by classical standards. What if Atlas is not simply a comet? What if its behavior reflects an environment or process that operates partially in the quantum realm, where superposition and entanglement are not abstractions but mechanical realities? The very act of observing such an object, measuring it with telescopes and spectrographs, would disturb its quantum states, potentially explaining inconsistencies between different observations, changes in brightness and composition that seem to shift based on how we look at it. This is not madness. This is extension of known physics into unknown territory. The observer effect, that central pillar of quantum mechanics, tells us that measurement itself changes reality. When we observe 3I-ATLAS, we are not passively watching it. We are interacting with it. We are collapsing superpositions, fixing properties that might otherwise remain in a state of quantum uncertainty. 2025 is the year when we learned we could teleport quantum information through existing infrastructure. What remains to be seen is whether the cosmos has been doing something similar all along, whether objects like 3I-ATLAS are cosmic quantum computers, manipulating their own states through entanglement and superposition, appearing strange to us, only because we are observing the collapse of possibilities into classical reality. Part 14. Fusion's point of no return. The Sun has been burning for 4.6 billion years, fusing hydrogen into helium, releasing more energy in a single second than humanity has used since the dawn of civilization. Every photon that warms your face, every ray of light that makes photosynthesis possible, every bit of energy that drives our weather and our oceans, all of it comes from fusion. Scientists have understood fusion for a century. What they could not do was repeat it on Earth in a controlled way that produced more energy than it consumed. That changed. On February 23, 2025, the National Ignition Facility in California achieved ignition for the 7th time in repeated experiments setting a new record. They fired lasers carrying 2.05 megajoules of energy at a target, and the fusion reaction produced 5.0 megajoules, nearly 2.4 times the input energy applied directly to the target itself. More recently, on June 22, 2025, a collaborative team led by Los Alamos National Laboratory, working with Lawrence Livermore, achieved ignition again, producing 2.4 megajoules in a self-sustaining reaction, a burning plasma that achieved critical conditions. 8.6 megajoules have been achieved in later experiments. The pattern is clear. Ignition is no longer a one-time accident. It is repeatable. It is scalable. It is becoming the baseline. How does fusion work? Two hydrogen atoms are pushed together with such force that their nuclei merge. The strong nuclear force overcomes electromagnetic repulsion. The new nucleus, helium, is slightly lighter than the sum of its parts. That missing mass, by Einstein's equation, becomes energy. Enormous energy. The temperatures required to achieve this, millions of degrees, can only be sustained in two ways. Inertial confinement uses lasers so powerful they compress a tiny pellet in a fraction of a nanosecond, creating the densities and temperatures of stellar cores for microseconds. Imagine taking the entire core of the Sun and compressing it into an object the size of a grain of sand. That is what happens inside the target chamber. Magnetic confinement uses electromagnetic fields to trap plasma, a superheated ionized gas, in a container shaped like a donut, holding it stable for longer durations. The National Ignition Facility chose inertial confinement. 292 separate laser beams fire simultaneously at a cylinder, called a hohlraum. Inside that cylinder sits a capsule filled with deuterium and tritium. The energy compresses it to 50 times normal density. Fusion ignites. Energy is released. The breakthrough is not just that ignition happens, it is that it is repeatable. It is becoming more efficient. In 2024, the facility achieved 120% energy gain on some shots. The trajectory is upward. Meanwhile, other groups are pursuing magnetic confinement. TE Technologies announced in April 2025 that their experiment, called NORM, has achieved their highest steady-state plasma performance, using only neutral beam injection without the complex quartz tube formation systems of earlier designs. This simplifies the apparatus dramatically. Think about what that means. Simpler apparatus means cheaper apparatus. Cheaper means scalable. Scalable means commercial. Commonwealth Fusion Systems, backed by over $2 billion in private capital, has completed assembly of magnetic confinement systems for their Spark reactor, expected to demonstrate net energy generation in the early 2027 timeframe. Private capital flowing into fusion means the market believes fusion is coming. Business does not fund mirages. Business funds the future. This is the point of no return. We are transitioning from proving that fusion is possible in principle to demonstrating that fusion can be commercially viable in practice. We have entered a regime where energy sources start to behave in fundamentally new ways. Classical physics says energy density increases with difficulty, with cost, with environmental impact. Fossil fuels require extraction, processing, transportation, combustion, and they produce waste and carbon and greenhouse gases that reshape the climate. Fission requires enormous safety infrastructure, cooling systems, waste storage, security protocols to prevent proliferation. But fusion exists in a different category. Two atoms merge, helium forms. The ocean provides the fuel, hydrogen isotopes dissolved in water. The waste is minimal, the energy release is absolute. Fusion does not produce carbon dioxide. It does not produce long-lived radioactive waste. It produces inert helium. It is the closest thing to magic that physics allows. Now draw a parallel. Just as fusion is challenging our foundational notions of what is possible in energy production, forcing us to rewrite economics and physics simultaneously, 3I-ATLAS is challenging our foundational notions of what is possible in small bodies. We thought we understood comets. We thought we understood what ice and rock could do under pressure and radiation. We had models, tested and refined over decades. 3I-ATLAS is proving that comets can be far stranger than models predicted. The velocity, the composition, the outbursts, the jets, all of it suggests that either our models are incomplete or something unusual is present. And here is the unsettling thought. What if the universe is entering a period where anomalies across multiple scales are not exceptions, but signals that we are only beginning to read? Consider the timeline. In 2022, fusion ignition was achieved for the first time. In 2023, multi-node quantum teleportation networks were demonstrated. In 2024, quantum teleportation over existing internet infrastructure was successfully performed, proving the technology could scale beyond the laboratory. And in 2025, we see ignition repeated, refined, moving toward commercial viability. Simultaneously, in 2025, 3I-ATLAS exhibits behavior that contradicts established models. These are not connected events in any causal sense, but they are thematically connected. They all suggest that the universe operates with greater flexibility than our current models allow. Energy can be released through fusion in ways we did not think were scalable. Information can be transferred through quantum channels alongside classical data. Matter can behave in ways that suggest hidden complexity or unknown mechanisms. All of this in a single year. All of this converging, the implications compound. Fusion will soon provide clean, abundant energy. With that energy, we can build quantum networks on planetary scales. With quantum networks, we can coordinate distributed sensing, distributed computing, distributed control of technologies we cannot yet imagine. And if objects like 3I-ATLAS are revealing that nature operates with hidden layers of complexity, then every new quantum network we build, every fusion plant we activate, every sensor array we deploy, might be tools for discovering what we have missed. We are not just building new technology, we are entering a new regime of physics. The universe is preparing to reveal secrets it has kept hidden for billions of years. Part 15. The big question. Are we entering a decade of rule-breaking discoveries? Reconsider everything. 3I-ATLAS arrived from interstellar space with a trajectory that suggested gravitational influence we cannot explain. The gravitational perturbations implied forces acting on the object that should not exist in the vicinity it was travelling. Its jet is continuous and coherent in a way that defies cometary models. Cometary outgassing should be chaotic, driven by localized heating, unpredictable in direction and intensity. Yet 3I-ATLAS produces a jet that looks engineered, precise, constant. Its composition shows materials that should not exist together under standard cometary formation scenarios. The chemistry does not match what we expect from objects formed in protoplanetary disks billions of years ago. Its brightness oscillates with rhythms that seem too regular to be accidental, too precise to be random. Its trajectory has drifted in ways that imply propulsion or momentum transfer beyond outgassing, beyond what physical processes we know can provide. These are not ambiguous observations. These are data points that falsify established models. They are not inconsistencies to be explained away or errors to be corrected. They are signals that something fundamental is different. Weave in the other discoveries of 2025. Dark stars are proposed objects where dark matter accumulates around primordial black holes, exotic objects that would completely alter our understanding of stellar populations and the early universe. If dark stars exist, the cosmos contains populations of objects we have never studied, objects that may outnumber ordinary stars by factors of millions. Quantum teleportation is now a practical technology demonstrated across metropolitan distances with high fidelity, proving that the laws of quantum mechanics are far more exploitable than physics textbooks suggested. Fusion has moved from theoretical possibility to repeatable demonstration of net positive energy gain, proving that energy production can be decoupled from combustion and fission and placed in the regime of stellar processes. And artificial intelligence is beginning to identify patterns in datasets that human researchers missed, discovering relationships in physics that conventional analysis overlooked. Machine learning algorithms trained on astronomical data are finding correlations that human eyes cannot see, anomalies that humans have been taught to filter out as noise. All of this points to a singular thesis. 2025 is not a year of incremental progress. It is the beginning of a paradigm shift. For 3 centuries, science has operated under the assumption that anomalies are errors, that models are approximately correct, that new observations refine existing frameworks rather than challenge them. This assumption worked well. It allowed us to understand gravity, electromagnetism, quantum mechanics, relativity. But what if that is wrong? What if anomalies are not noise but signal? What if models are not approximately correct but fundamentally incomplete? What if the universe is far stranger than our current categories allow, and we are only beginning to perceive the strangeness? What if we have been filtering out signals because we were trained to see them as noise? Think about what we call natural. A comet is natural. Ice and rock in space, ejected from a star system drifting between worlds. Fusion is natural. It powers the sun. It forges elements in stellar cores. It is one of the most fundamental processes in the universe. Quantum entanglement is natural. It is a demonstrated feature of quantum mechanics. It has been tested and confirmed countless times. But 3I-ATLAS might be natural too, if we expand our category of natural to include phenomena we do not yet understand. What if being natural no longer means conforming to our current models? What if being natural simply means existing without deliberate human intervention? By that definition, 3I-ATLAS is natural. It came from the stars. It is not artificial. It is not engineered by human hands. Yet it behaves in ways that contradict everything we thought we knew about objects in space. The deeper question becomes, are we undercounting phenomena that do not fit neat categories? Astronomy catalogues objects as stars, planets, asteroids, comets, black holes, neutron stars, brown dwarfs, each a box with properties and behaviours. We put objects into categories and we study the categories. But what if there are objects that span multiple categories? What if there are processes that operate across scales we have not examined carefully enough? What if 3I-ATLAS is the first of many discoveries that will not fit existing boxes? What if the universe has been showing us these objects all along and we simply did not have the tools to recognise them? Consider the cascade of implications. If dark stars exist, the universe contains populations of objects we have never studied, with properties and behaviours completely unknown. We would need to rebuild our models of galactic structure, of stellar populations, of the early universe. If quantum teleportation can operate through existing infrastructure, secure quantum networks can be deployed globally, enabling technologies we cannot yet predict. Communication systems will be transformed. Computing will be transformed. Science itself will be transformed. If fusion achieves commercial viability, energy scarcity ends, and every technology limited by energy becomes possible. Climate change becomes solvable. The global economy transforms. Materials science transforms. Space exploration becomes affordable and practical. If anomalies like 3I-ATLAS are not exceptions but representatives of a larger class of undiscovered phenomena, then our models are not complete by degrees but missing entire categories of physics. We are not just refining our understanding, we are discovering that the universe has dimensions we did not know existed. What will the Hera array reveal when it tracks 3I-ATLAS? What will the Europa Clipper spacecraft send back if it encounters this object, or others like it in the deep solar system? These are not idle questions. They are about discovering what being natural means in a universe we are only beginning to understand. The data collected in the coming weeks could reshape our conception of comets, of propulsion, of what small bodies in space are actually capable of doing. It could reveal that 3I-ATLAS is a precursor to discovery of a new class of objects entirely. It could show that anomalies are not exceptions, but a signal that we have been modelling the cosmos with dangerous incompleteness. The universe may be trying to tell us that our maps are missing entire continents, our physics textbooks incomplete, our categories too narrow. Here is what must be understood. Every great discovery in history followed this pattern. An observation that did not fit the model, dismissal as error or anomaly. Continued observation and measurement, realization that the model itself was wrong. Newton was wrong about gravity but only slightly. Einstein corrected it. Maxwell understood electromagnetism, but quantum mechanics showed that light and matter were more entangled than classical physics allowed. Each generation discovers that the previous generation's models were incomplete. Ptolemy thought Earth was the centre. Copernicus was right. Kepler refined the orbits. Newton explained the force. Einstein added space and time. Dirac predicted antimatter. 2025 may be the year when we discover that our current models of comets, energy, information, and the nature of the cosmos are not just incomplete, but missing entire dimensions of physics. The universe is not broken. Our understanding is. So stay tuned, watch the data, scrutinize what Hera observes, monitor what interplanetary probes report. Listen to what artificial intelligence discovers in the datasets we cannot manually analyze. The universe is about to tell us something we did not expect. It always does. 3I-ATLAS is just the first voice in a conversation that is about to get very loud. In the coming months, we will learn whether our models hold, or whether reality is stranger, deeper, and far more wonderful than we ever imagined. The next chapter of physics is being written now. Pay attention